the stuff I was doing in the last lecture. So we are talking about how to create tables that are in normal form. So if you're given one large table with all the attributes, how do you split this one large table into several tables? Because if you have just one large table, there's a lot of redundancy. So you have to divide into smaller tables. So how do you do that? So, so we spoke about functional dependencies. So I want to continue. So when you start designing a system, you get all the attributes and you're given a set of functional dependencies. So one of the things with functional dependencies is whatever functional dependencies that you initially come up with, try to minimize it. So let me give you an example. So this is, so minimize the functional dependencies. So let's say we are given a set of functional dependencies. So I'm going to try to stick with the, some form of the company database. So name, manager, D number. Then you have FD2. D number goes to D name, manager. FD3 goes to P number, which goes to P name, number. Okay, so remember that when you are first in the design process, when you are trying to pin down all the functional dependencies, when you look at these functional dependencies, you can see that there are, in the functional dependencies, there are some redundancies. So for example, you're given that D number goes to D name and manager. And then out here in this table, you have both D number and you have manager. But you know that from FD2, you know that D number determines manager. So you can rewrite this functional dependency. So we can say set2 would be okay, so remove that D number determines manager because it's there right in FD2. So we have okay, and then if you look again at this next one, again, you have the same thing, D number going to manager, so remove that. And then in FD4, we have D number is again repeated out here. So we have, we have this. Because you already have that out here in FD3, so remove that. So we have FD4 is equal to okay, so that's one of the first things when you are in system design, when you have a set of functional dependencies, look at the functional dependencies and see if you can minimize this set. So it's better to use when you are trying to divide the table into smaller tables, that is, you're trying to find normal relationships, look at the functional dependencies and clean it up, and it's much easier to do the next step once you do that. And set1 is equivalent to set2. But so set2 is cleaner, so use that. So I want to give a few more examples before I start up with third normal form. So suppose we have this table with attributes A, B, C, D, and E, and you're given the functional dependencies. AB determines C, AE determines D, and D determines B. So I would like you to figure out which of the following are true from the above. So AD goes to C, ADE goes to BC, and ABC goes to D. So I want you to try this out. Which of these three functional dependencies hold given this problem?
Yes.
Yes, so if you do the closure of attributes from AD, you know that D determines B, so you can bring B in here. And then AB determines C, so you can bring C in here, so it does hold. And so the next one, so this is correct. Let's look at the next one, ADE. I think this is rather easy. So we have A, D, E, and then D goes to B, and then AB goes to C. So yes, this one holds. And then you have ABC, BC, E goes to D, D goes to B. So that's, yeah, so the last one doesn't hold because from ABC, you can just get ABC. It doesn't determine anything else. Okay, so I mean, so if you're given questions like this, that's how you find out. So let's try one more example. So we have AB goes to C, C goes to D, and BD goes to E. So what I would like you to find out is whether A, B, C goes to E, AB, whether that goes to E, and whether AC goes to E. So just try out these three. Okay, so again, on this one, I hope all of you had a chance. You can get the first one, you can get the second one, but with just AC, you cannot get E. So I mean, as long as you understand how to do it, I mean, I just want to make sure you understand. So, so now that you have an understanding of functional dependencies, so the next thing I'm going to talk about are how to reduce a table to normal forms. So so just summarizing what I did in an earlier class, there are several normal forms. So there's first normal form, second normal form, third normal form, Boyce chord normal form, fourth normal form, and fifth normal form. Okay, so in this class, at the very minimum, when you are designing databases, at the very minimum, you have to bring it down to the third normal form, at the very minimum. Um, um, it, it would be a terrible design if you do not kind of bring it down. I would say that third normal form, I mean, unless you have very very extraordinary reasons for leaving it at second normal form, generally is recommended that you at least bring it down to third normal form. So in class, I will not be doing first normal form, second normal form, and the fifth normal form. I think there's no need to go up to the fifth normal form tariff. So, but it is given in your textbook, and in PowerPoint slides, I have put up first normal form and second normal form. I don't know whether I did fifth normal form. So you can look it up on assignment problems. I think I would give assignment problems with second normal form. So I definitely want you to know what it is, but you can read that up. I'm going to start with the third normal form. And again, I had, like I mentioned in class, all these normal forms are related. We have so we have fourth normal form is, okay, and then Boyce Codd normal form and third normal form. So if something is in fourth normal form, it is also in Boyce Codd normal form and third normal form. If something is in Boyce Codd normal form, then it's also in third normal form. So as you climb up this thing as you go, so if you have something in fourth normal form, you know that all the other normal forms, it follows. So each normal form is stronger than the previous one. So all the problems that we are going to do is you're given an input, and the input is a relation R with all the attributes. So we have R, A1, A2, and so on. Okay, so we have all the attributes, and you are also given all the functional dependencies on the attributes. Yes, sometimes the functional dependencies are not the minimal set. If they're not the minimal set, minimize it. But you are given all the FDs. And so I'll be doing all these different algorithms. So the whole idea is that once you're given this, once you run an algorithm, so the output is going to be a set of normalized tables. So from R, you'll get R1, R2, and so on to, let's say, Rn. And they're such that you can get the original relation R from R by joining all these tables together. And this original table R, that once you join these tables together, there are no inserts. So that's very important, because if they're not normalized, you might have all those anomalies that I showed you in an earlier class. So this is such that there are no insert, delete, update anomalies. So it's a lossless join. So you're not going to lose any data, and nor are we going to get any false tuples. Okay, I'm going to start with the third normal form, and I would like you to look up in the PowerPoint slides or in the textbook for the first normal form and the second normal form. But I'm going to start with the third normal form. So I'm first going to give the definition of the third normal form. So a relation R is in third normal form if for all functional dependencies. Okay, so I'm going to write in a short form. So for all functional dependencies, A going to B, and I'm going to write this line on top because it's a real pain to keep writing. So A means it's equivalent to saying A1, A2, A3, and so on to, and B means is a short form of saying B1, B2, B3, and so on. So essentially what I'm saying up there is A1, A2. So these are all the attributes on the left side. Oh. And so on. B1, B2, B3, and so on. So that's what I'm saying, but it's real, instead of keeping on writing like that, I'm just going to put a bar on top to indicate it. So a relation R is in third normal form if for all functional dependencies, A bar going to B bar, one, A bar must be a key of the relation or a super key. Okay, so we did super keys in the last class. Super key is just a key with some more attributes thrown in. It's not a minimal key. So if you have a functional dependency, then A must be the key or a super key. And the second is, or if A is, so either A must be a key or a super key, or B must be a prime attribute. Do you recall what a prime attribute is? I did this in an earlier class. Does anyone remember that? What is a prime attribute? So a prime, so this you must remember, this prime and non-prime. A prime attribute is an attribute that is part of a key. So B must be part of a key. Or okay, so that is a relation in third normal form is one where either for all functional dependencies, either the left-hand side must be key or super key, or the right-hand side must be a part of a key. So let's take a look at an example. Okay, so we go back and look at our example, the social security number, name, D number, manager, and D name. And we are given the following functional dependency. So I'm going to use the short notation that's given in the book. It's a kind of like a diagrammatic notation. So okay, so the first functional dependency, FT1, is that social security number determines the name, DNO, manager, and D name. And the second functional dependency is D number determines manager and D name. So that's FT2. Okay, so these are the two functional dependencies given. So the idea, so what we have to find out is this relation R in third normal form? So in order to find out whether R is in third normal form, you first have to see what is the key. So the key for the relation, so the first thing is, what's the key? So, and that's really easy from the functional dependency one, you know that SSN, the key is SSN. So SSN is the key, right? So now, so there's no problem with functional dependency one. Functional dependency one is perfectly fine because the left-hand side is a key. So now we look at functional dependency two, where you have D number going to manager and D name. Now, but D number is not a key, and nor are manager and D name prime attributes. So therefore, relation R is not in third normal form. So you have D number going to D name and manager, right? Yeah, but that's FD2. D number is not key, and nor are D name, manager, prime attributes. So therefore, R, so this will imply that R is not in 3NF. Okay, so so R is not in third normal form. So the idea is that so if R is not in normal form, that means that there is redundancy in this table, and you can look at it because if you have 10 people in department number 5, all you have to write manager and dname 10 times. So this is not a good design. So you need to divide R into 2 tables. So that are in third normal form, R1 and R2. So in order to divide it, we are going to use the following algorithm. It's the third normal form decomposition algorithm. So it's a 3NF decomposition algorithm. And so the algorithm is, the input is R with all attributes, and all FDs. Okay, so then what you do, there are 2 steps. So step 1, first you compute the key of R. Using the closure property that we did in the last class. So compute all the keys of R, because if you have candidate keys, those are keys too, you could have. So compute all the keys of R using the closure property of FDs. And then step 2, repeat until all relations in third normal form okay. So A, pick any R dash with functional dependency A going to B that okay, so you pick any relation R dash. So initially you've set R goes to R dash. So pick any relation R dash with a functional dependency that violates third normal form. So that's not a normal form. And then B, divide R dash into R1 dash, which is AB, and R2 dash, which is A, and R dash minus B. Okay, so you're dividing the table R into 2 tables. So R1 dash, which is the attribute that violated that third normal form, and R2 dash is you bring down the key, the left-hand side, into this table, and then bring down all the attributes except B star. So let me just B bar. So let's just go back to that earlier example. That was this example where we have D number, that is FD2 that is violating the third normal form. So what we do for this earlier example, so going back to the example, so we had FD2 that was violating, right? FD2. So what you do is you have the first table R1 dash, which is D number. And we had D name and manager. Okay, so that's the first table. So for this table, D number is the key actually. We know that D number goes to D name and D manager. Okay, and then you have the second table, R2 dash. So in R2 dash, you have to bring down this D number, the left-hand side. So you have to bring this down. And then you have all the other attributes in the original table that was not there in the original. So we have SSN and name. And the key for this table is SSN, and you have okay, so now the table R is divided into two tables, R1 and R2 dash. So we have
wouldn't R minus the B bar be already have DNO in it?
No, so that's the thing you have to bring down. So that's the main thing is that the A you have to bring you have to bring down the A bar. So you have to bring this down. The key, the left-hand side of the functional dependency, you have to bring it down. So D number was the left-hand side, so you have to bring it down.
Yeah, but what I'm saying is the original relation would already have DNO in it. So when you say R minus B bar, DNO would already be in that relation, wouldn't it?
Oh, you mean that? Yeah, I got what you're meaning. Yes. Minus B bar. I guess I just wanted to make sure that you bring down A bar. Yes.
Okay, that makes sense. Yeah.
Yes,
Yeah.
you're right. I have a redundancy out here. I should actually write. R2 is equal to.
Yeah, I get what you were illustrating.
Yes. You can just write R minus B bar. You can actually just write that down. You're correct. But I just want to really specify that you have to bring down the left-hand side. So okay. Maybe I should say R bar minus B bar minus A bar. So this is just really important because there has to be an attribute that links the two tables. So if I just write this down, I'm scared that people will forget to bring this one down. But it's a very good observation. So maybe I should actually correct this and write. Oh. Yes, because I've already put A bar on the other side, but I guess it makes it more confusing. So just let's leave it the way it is. Oh, it's 10 o'clock. So that's how you, so I'm going to continue with this in the next class. Does anyone have any questions?